So share my desktop with you. Okay, so today we're going to talk about the homework and review problems for test 3 and Monday's test. So first thing, let's talk about Monday's test. It'll be split into two groups. Group 1 will be from 12 to 2, group 2 will be from 2 to 4. Here's the people in those groups. Joe Barry, you're in group 1. Claudia, you're in group 2. So it'll be multiple versions of the test, and I'll use Zoom to monitor you. So I'll just, you'll get on Zoom and show me your test paper and everything. It'll be on paper, so I can more easily give you partial credit and whatnot. Just, take a picture with your phone and drop it in a Moodle. It'll cover normal distribution and, normal CDF, inverse norm, all that good stuff, and confidence intervals, Z's, T's, and P's. And if you look at the review, it's basically the test just with, different numbers. Okay. So first thing I'm going to do is go through the homework problems and just identify whether they're a Z or a T test, because, well, that's the most important thing, being able to identify whether they're a Z or a T. So if we look at this one, reading it, we're not given the population standard deviation. What we are given is the sample standard deviation. That makes this one a T test. Okay. Oh. Where do we find the review? Yeah, it's on Google Drive. So the review is on Google Drive. If you go, I'd highly advise sorting by date. That way you can find stuff easier. And it should be at the top. Stats test review number 3, right here. Stats test 3 review, normal distribution, confidence levels. So we'll go back and do a few of the homework problems. We're not going to do them all because we need to get through the homework and review problems. So first thing we're going to do is just identify whether they're Z's or T's and write down these hypotheses, and you can go from there. So we're going to test the claim that the mean change is positive. Okay. So positive values represent improvement. Well, to be positive, we have to be greater than 0. So if I write down my hypotheses, positive would be the mean is greater than 0. That goes in the alternative. And the mean being less than or equal to 0 will be our null. And your statistics are right here, so that gives you what you need. Let's look at the next one. Sorry, I need to change the size a little bit. Okay. Sample of 106 body temperatures with a mean of 98.20 degrees Fahrenheit. Assume the population standard deviation. There we go. Population standard deviation is known to be 0.62. That sigma is 0.62. That makes this a Z test. Okay. So this one you need to do the Z test on. The first one you had to do a T test. This one's a Z test. Again, I'm going to write down the claims and the hypotheses. Population is less than 98.6. That's one right here in the alternative. That's where my claim is. And then greater than or equal to would be my null. So the first homework problem was a T, and we had to, our claim was in the alternative, and it's a right tail. Second one's a Z, claims in the alternative again, and it's a left tail. Check number 3. Okay. So let's see, they have a mean, so these supermodels have a mean height of 70.2 inches and a standard deviation of 1.5 inches. That's for the supermodels. That's not for the population. Does it say anything about the population or women or any of that? These particular supermodels have a standard deviation of 1.5. That means S is 1.5. That makes this a t-test. Okay, looking at our hypotheses. Oh, no, question. Oh, just you and me, Claudia. Claim that supermodels have heights with mean that is greater than the mean of 63.6. Yeah, Jared's internet's cutting in and out, he says. Greater than the mean. So greater than the mean. That would be our alternative. That's what our claim is. It's going to be a right tail. Less than or equal to would be the null. Okay. So there's the hypotheses. This is a t-test. Again, you can read the problem for the relevant information, and we'll work a few of these. But first, let's just go through all of them and see what kind they are. Okay, let's read this one. Let's lower the measured amounts of lead in micrograms per cubic meter in the air. EPA, blah, blah, blah. Let's see. I don't see anything saying anything about any standard deviation, but we do have a data set. Okay, so it doesn't give us the population standard deviation. It does only give us the data. So from here, we're going to have to find X bar and S. That makes this a t-test. We don't have sigma, it's a t. That looks kind of like an A. So let's look at our hypotheses. So this is definitely one of the ones I do, a data one. Use the 0.05 significance lower test to claim that the sample is from a population with a mean greater than 1.5. So another greater at the right tail. And of course, this is where the claim is, because that's what they say they're claiming. They claim that a sample is from a population with a mean greater than 1.5. Okay, let's see what kind this one is. An axial load of aluminum can is an important measure. Top loads are pressed on with really high pressure. Pepsi used thinner cans, and a random sample of 175 thinner cans has a mean axial load of 267.11 pounds. That's X bar. The standard cans have this mean and this standard deviation. Okay. Use a 0.01 significance load to test the claim that thinner cans have a mean axial load that is less than 281.81 pounds. Assume that, I think that was supposed to be a sigma and it got translated. Let me go look. So, yeah. This is let's see if we can find it. Thinner cans weaker. Yeah. Do thinner cans. Assume that sigma. Yep. Okay. We wouldn't assume the sample standard deviation. We calculate it. That's why I kind of was curious about that. So assume sigma is 27.77 pounds. So that one kind of was a typo, translating from one document to another. Sorry. But this would make it a Z test. However, if you did it with S, that would be a T test. So whichever way you did it, I'm going to triple check, because I did double check these. I'm going to triple check on the test and make sure there's no typos like that. In fact, I'm going to change that right now on this one. Oops. Oh, wait, that's the review, sorry. So that makes this a Z test because that was the sigma they gave us. Assume sigma is 27.77. Do thinner cans have a mean active load less than 281? So that would be in the alternative again, 281.81, that's the claim. Greater than or equal to would be null. So that would be a Z test for this one. So let's go ahead and do a couple of those. I'm going to do this one. Let's go ahead and start with this one. So this one involves a data set. This is problem number 4, I believe. So let's write down the information. N is 1, 2, 3, 4, 5, 6. S and X bar, we need to calculate. Okay. Alpha, 0.05. Right there. And let's just grab our calculator and see what happens. So I'm going to go to mode, that one variable. Do that again. Mode, number 3 for stat, number 1 for one variable. Type this stuff in there. And I have 6 data values, so that's looking good. I'll hit AC to get out of there. And then I'm going to go to shift number 1. Need those variables. I need X bar and I need S. We don't want sigma. That's not what we need. That's estimating sigma. We don't do that. We're going to use number 2 and 4. So first, I'll grab X bar. 1.53. Let's go. The data is to 2 decimal places. I'm going to go 3 decimal places. 1.538. And for my actual calculations, I'm going to store that value. So shift, so A. So now I have my mean saved as the letter A. Then I'm going to go to shift 1, number 4 again, number 4 again, SX. That's 1.914. I'm going to store that one, shift, so B. So now I've got S and X bar saved in my calculator. I don't have to worry about rounding issues. And then we're going to calculate the test statistic. It's a T distribution, so I'm going to use the T test statistic. If you don't remember, right here in your formula sheet. Okay, and then we just plug in the numbers. So I'm going to write 1.538, but in the calculator, I'm going to use the letter A because we saved X bar as A. So I don't like to round until the very, very end if I can help it. If you're using a crappy old basic calculator, then you'll have to round. And N was 6. So this would be my test statistic here. Let's see what it pops out with. Go to mode 1, type it in. So I need a fraction. And I'm not going to actually do this one. I'm going to type in A. A minus 1.5 over B over square root of 6. So I saved X bar as A, I saved S as B. So those have those, well, the best values I can, the most digits in there. And I get 0.0490. Or 0.049, it's 0.5, so I'm gonna put 1. And now we're gonna use this number. We can either do traditional or the p-value method. We're gonna do both. So I'll start with the traditional method just because for the t-test, I think the traditional method is a little easier. So my center is always 0. This is a right tail test. That's 1 tail, and alpha is 0.05. So I'm gonna look at my critical value. It's a right tail, so I'm only gonna have 1. It's gonna be positive. So it's area in 1 tail, and alpha is 0.05. So that's what I'm gonna look up. Area in 1 tail is 0.05 right here. Now I need my degrees of freedom. N is 6, so my degrees of freedom is n minus 1, which is 5. So right in this row here, this column, boom, 2.015. That's my critical value. So I'm going to plot that. 2.015. The right tail, so I'm going to shade to the right. Going to plot my test statistic. 0.04. I'll stick it right there. And we can see that it's outside of the rejection region. So I'm going to fail to reject the null. Okay. All right. So my test statistic was 0.0491. That means it's between 0 and our critical value. So it's outside of the rejection region here. It's outside of the rejection region. We don't reject the null. Looking at the p-value, we're going to look for our test statistic using this right here. So I'm going to look on the 5 degrees of freedom, that row. It has to be the same degrees of freedom. I'm going to look for 0.04. Well, I'm not going to find it. So it's to the right of this number right here. And as we can see, from left to right, the alpha is going up. So if it's to the right over here, it's greater than 0.10 in this case. So what I can say is the p-value is greater than 0.10. Again, without TI or some other calculator that can do these, you're not going to be able to get the exact p-value. You can just say, is it bigger than or is it less than, whatever, between these two numbers. So p is greater than 0.10. So p is definitely greater than 0.05. So p is greater than alpha. So again, we fail to reject the null. TI users, I'll go ahead and run through this one real quick. So stat, edit, kind of the top up here, clear that. 5.4, 1.1, 0.42, 0.73, 0.48, and 1.1 again. So I'm going to quit out of there, go to stat, tests. It was a t test, number 2. I'm going to highlight data, hit enter. It asks for mu, that's 1.5. And I typed it in list 1, always keep frequency as 1. It's a right tail test. You get that from the alternative every single time. And we calculate. It tells us p is 0.48. Well, 0.48 is definitely bigger than 0.1, so we weren't wrong there. And it does give us the same value for the test statistic. And our mean and standard deviation are also given to us. So if you do have a TI, I suggest using it. It's a lot easier. Either way we do, p-value or traditional method, we're going to fail to reject the null. So to write our final conclusion, the claim was in the alternative. There is not enough evidence to support the claim that the sample is from a population with a mean greater than the EPA standard of 1.5 micrograms per cubic meter. So that would be the conclusion, and that would be the answer. On the test, well, this will be on test 4. On the test, I will expect to see all of this. Again, it'll be on paper, so I will expect to see critical values and p-values, both. Claudia, any questions? Okay, guess not. Let's see, that was a right tail. Let's look at a left tail. Do I have any with the claim and the null? I don't. So we did these last week, so I'm just going to do a couple T problems. I'll do this one next. It's nice enough to give us the info, so I'll use it. And it's 21. This is problem number 1, I do believe. X bar is 4.00. Again, those 2 zeros do matter for significance. In statistics and science, accuracy matters, precision matters. So we need to have as many decimal places as possible. So 4.00 is different from just a plain old 4 in that respect. All right, alpha, what's that? In this case, 0.01. So we got all the information. Now we're going to calculate the test statistic. Having fun? Hold on, it's not wanting to map. So again, well, here's the formula. It's on your formula sheet. Please make sure you have your formula sheet. You can print it out. I suggest printing it out so you can have a physical copy of it. I did print one for you, so hopefully you still have it. I'm sure you do, Claudia. Talking to anybody else that actually watches this video, if anyone does. So X bar, what's that? It's 4 point nothing. And our mean, we said it needed to be positive, so that's going to be 0 for our mean. That's going to be a big statistic. 2.17 for our sample standard deviation, square root of 21. Casio, let's pop it in there. 4, just do 4 because 4 minus nothing is still nothing. 2.17 square root of 21. 8.44, yeah, 7.1. Yeah. So it's greater than, it's a right tail. I'm pretty sure it's going to be in the rejection region, regardless of what alpha we use. But let's just draw it and make sure. So there's my center. Let me find out what one tail alpha 0.01 corresponds to. T distribution, okay, one tail 0.01 for alpha, yeah. How many degrees of freedom do I have? N is 21, so I have 20 degrees of freedom. Pop down here, here's 20, yeah, 2.5, that's okay. So my critical value is 2.528. Let's stick that on here, and let's stick it right about there. Not that close. Right about there. 2.528. Oh, yep, go ahead. Let's see. Can you explain degrees of freedom? Okay, for our class, degrees of freedom is always just gonna be n minus 1. Always. It's based on how many variables you can assign freely. In a 2-sample population, we'd have to take n minus 2 because we'd have 2 variables set. But without this class, we're just doing 1 variable. It's just gonna be n minus 1. This is n minus 1 gives us our degrees of freedom. Minus 1 is 20. Good. How do you use that to find the critical value? Okay. So if we look at our chart, the left column is degrees of freedom. So we need to be in that row that corresponds to our degrees of freedom. We have 20 degrees of freedom, so our critical value is somewhere in this row. So then we look at our alpha value. Our alpha value is 0.01. I kind of drew over it. That's 0.01. It's a right tail. So 0.01 right tail. Right is one tail. So 0.01 here. So this column, this row, that makes it this value right here, 0.2528. So degrees of freedom gives you the row number. Your alpha value gives you your column number. Any other questions?
Nope, I got it.
Cool. All right, so there's that. I'm going to shade to the right because it is a right tail. And then if I look at my test statistic, 8.4, I think that's bigger than 2.5, I think. If I'm not mistaken, so I'm going to stick it in there. Yep, that's going to be rejecting via null. Okay, let's look at this in terms of a p-value. So we already know what our answer is going to be. We've rejected the null, we can set our conclusion. That's the traditional method. I want to also look at the p-value method. We already get the p-value. We're going to look in the row that our degrees of freedom are, so somewhere in this row. We're going to look for our test statistic. It's either going to be between 2 numbers or on the outside of 2 numbers. We're never going to get the exact number. So 8.4, let's see where that's going to be. I think, yeah, I'd have to say it's to the left over here. It's to the left of 2.8. Notice our values are going down as they go to the left. So for our p-value, we can't say exactly what it is, but we can say it's less than 0.005. That's the same first to the left, and we know it's more or less than that. So that means p is definitely less than alpha. So we're going to reject the null there. Okay, let's grab the TI. We can see exactly how much less the p-value is than 0.005. I'm pretty sure it's going to be really tiny. Might even get a straight 0 for this one. So we're going to go to tests. It's a t-test, number 2. This time we're dealing with statistics though, so we're going to hit enter there. Mu was 0. X bar was 4. S was 2.17. N was 21. And it was a right tail. Yeah, right tail. Calculate and, oh, no. It's P is 2.4, except there's 7 zeros in front of that. So 0.000000002. That's what P is. And yeah, that's less than 0.005. So we're good there. And of course, it does give us the same value for the test statistic. Okay. We've rejected the null, the claims, and the alternative. So again, there's not enough evidence to support the claim. And then whatever the claim said. The mean change is positive. I'll put it there. And that would be that hypothesis test done. And we'll look at the hypothesis test again on the test 4 review, but I want to go ahead and look at the test 3 review, since that's what's coming up next. Again, there won't be a quiz this week. We're just going to forego that. You'll be tested on hypotheses on test 4, not next week, but the week after. So let's look at the test 3 review. So there's 2 things we're dealing with here. We're dealing with the normal distribution, normal CDF, inverse norm, all that good stuff. And we're dealing with confidence intervals, the more P, V, and T stuff. I think I will go through most of these, but I'm going to do them rather quickly. These should seem familiar to you. They're directly taken from your quiz problems. So I already have the problems randomly generated, so that won't be an issue. Women's heights are normally distributed, and however, there were some that weren't doable. I'm not going to do that on the test. They're all going to be perfectly fine, doable, don't meet the conditions. I'll either say they're normally distributed, or I'll make sure N is greater than 30. So women's heights are normally distributed with a mean of that. I'm going to start writing down my information. And a standard deviation of 2.5. This is talking about the entire population of women. That's why we're going to use a sigma. If one woman is randomly selected, you could write N as 1, but really we only care when N is greater than 1, because that's when we have to apply the central limit theorem. What is the probability that she is a midget? To be considered a midget, her height must be less than 58 inches. So X is less than 58 inches. Sketch the curve and determine the probability. So here we go. Let me get that line out of the middle. Put it down here. So our mean goes in the middle. Sketching the curve here. We want to know the probability that she's a midget, the probability that she's less than 58 inches. So I'm going to stick that over here, because to the left is 63.6. And it's less than, so I'm going to shade to the left. So same kind of thing as when we're doing hypothesis testing, it's just here we're calculating probability. And if you remember, probability is the area under the curve. Now you can use the chart for this, but we'd have to convert it to a normal score. We'd have to convert to a standard normal score. You can also use the Casio or the TI using a normal CDF. I'll do it all 3 ways, starting with the Casio. Okay, so I need the area to the left of 58. So So I'm going to go to mode down number 3 for distributions. Normal CD. Lower bound, negative infinity. So on these, it is important that you hit this times 10 to the button. If we don't, then that could give us some issues. So -1 times 10 to the 99. Okay. The upper bound would be 58. The standard deviation is 2.5. And mu, 63.6. So there's our probability right there, 0.0125. We're going to go 4 decimal places on these. And that would be the answer, the curve sketch and the probability. That's both questions answered, done. Now, if we're doing it using the charts, we first have to convert this to a standardized score. I think we use the test statistics formula. I don't think they have a separate one here. Let me check. Oh, yeah, they do. So it's basically the same thing if you look at the test statistic formula. The only thing here is they automatically apply the central limit theorem to it. Here they don't unless we actually need to use the central limit theorem, then we just stick it in there and it will be the exact same formula as the test statistic formula. So if we look at it, so this is for doing it by hand without any calculators, or without a good calculator. Our z-score is going to be this, x minus mu over sigma. So 58 minus 63.6 over a sigma of 2.5. Make sure I'm load 1. 58 minus 63.6 over 2.5. And we get that, but we really need this, negative 2.24. And we need to find the area to the left of this value. This is a Z chart. We're looking at Z for the normal distribution. So all of these are going to be Z's. Negative 2.24. Negative 2.20123 right here. Yep. So 0.0125. So same thing we got here. So it was a left tail, and the chart automatically gives us the left tail area. If we needed the right tail, we do 1 minus this value. If we needed it in 2 tails, well, that's a confidence interval. We cut it alpha in half. That's later. We'll get to one of those. TI users, same kind of thing, just stick it in a normal CDF. To get there, you go to second bars, number 2. Lower bound, upper bound, mean, and standard deviation. 0.0125. Done. That's it for that problem. Shouldn't be too bad. I'm pretty sure everyone either has a TI or a Casio, so you can just use the normal CDF on that. Okay. 20% of plain M&M candies are orange. Among 100 M&Ms chosen, 25 are orange. So assuming that the plain orange M&M's rate of 20% is correct, use the normal approximation to the binomial distribution to estimate the probability of randomly selecting 100 M&Ms and getting 25 or more that are orange. Don't forget your continuity correction. So if we go to their Google Drive, this is probably something you've forgotten about. It's down here. March 19th is whenever it was stuck in there. Continuity correction. Let's see it pop up any minute now, or day or year. Okay, let's come back to that. Open. And if it won't open for you, just download it. Yeah, we should be able to open it from download. That's not what I downloaded. Okay, weird. That's okay. We'll get it. One way or another. Let's try this one. There it is. So I took a picture of this and stuck it in the Google Drive. That's what we need to be looking at here. I'll stick it right there. You can also take a picture of it and make sure you have it. So whenever we're approximating the normal distribution, whenever we're approximating the binomial distribution with the normal distribution, we have to fix our x value. So let's look and see what we got here. So in 100 M&Ms, 25 are orange. So that makes p hat 25 out of 100. P would be 0.2. And when I estimate the probability of selecting 100 M&Ms and getting x is 25 or more. So x is not equal to, it's actually greater than or equal to. So if we look at our continuity correction, if it's greater than or equal to, we have to subtract 0.5. So right here, instead of using x is 25, we're actually going to use 24.5. That's going to be our lower bound. Because remember, we're turning this into a normal distribution. That's going to be our lower bound. Our upper bound is going to be infinity. Okay. Now, if we remember, or if we don't remember, we can look on the chart. NTX, where is it? Gives us our mean and our standard deviation. There it is. So the mean is n times p. The standard deviation is n times p times q. So in this one, we're not worrying about this 20%. We're worrying about what actually happened. So we don't even care about this one. We just need that. So mean is n times p, and q is going to be the complement of that, 25 out of 100. And let me test that. We might have to use p as 0.2. It's been a little while. So let's see what we get here. For the mean, yeah, we definitely need to use the 0.2. So if we look at these, we use the 2/3, the actual. So we use the p, not p hat. That makes q 0.8. Sorry about that. So we're going to use the p and the q, not the p hat. The p hat is what gives us x. We don't even need p hat for these things. Got our chapters mixed up in my head in a minute. So n times p, well, that's 20. N is 0.2 times 100, 20. Square root of n times p times q, so multiply that by 0.8, and take the square root of that, is 4. The square root of n times p times q is 4. N times p is 20. That's my mean and my standard deviation. That's my lower bound and my upper bound. Let's see what the calculator gives us. Again, we're going to go to the normal distribution, down 3, normal CDF, number 2. Lower bound is 24.5. Upper bound is infinity, 1 times 10 to the 99. Standard deviation of 4, mean of 20. So we get a probability of 0.1303. For that one. So there will be one of these on the test. Make sure you use P and Q, not P hat. We don't worry about P hat on this part. That's the next part. So we use P and Q, not P hat and Q hat. Just read, see what kind of thing you're doing. 25 or more, that's greater than or equal to 25. That tells you to either subtract or add the 0.5. Okay. So let's look at the next one. The elite school only accepts applicants who score in the top 2.5% of the ACT. It was reported the mean score of the ACT was 21 with a standard deviation of 5.4. What is the minimum score required to get into this elite school? So basically, we're just converting this. Let's draw and see what's actually going on here. They take the top 2.5%. So if this is 2.5%, that's the right tail, is 2.5. 97.5 would be the left tail. That's the area to the left. And since the chart gives the area to the left, that's what we're going to be looking at. This is the Z score. So alpha is not 2.5, but 1 minus the 2.5%. That's 0.975. That's what we're going to be looking for. And the mean is 21. Standard deviation is 5.4. I'll show you this one all 3 ways, starting with the Casio. So go to mode. It's a distribution. And we're not looking for an area. We're looking for a score. So we're going to do an inverse normal. So the area is 0.975, not 0.025. The standard deviation, standard deviation is 5.4, and the mean is 21. So 31.58 So the z-score would be 31.58. However, you can't have a 0.58 on the ACT, so it's 32. So that would be the answer. It would be 32. To do it by hand, you first convert this thing to a z-score. So if we use our formula, a little bit of algebra, we can get it. I don't know if they might actually have the formula for us. We can just rearrange this one for x. And that's what we'll do. So we rearrange this formula for x. Oh, this one. Z equals x minus mu over sigma. Do a little bit of algebra. X equals z plus, or z times sigma plus mu. It's a terrible mu. Multiply both sides by sigma, add mu. Done. This is the formula. To get sigma given to us, mu is given to us. What's not given to us is the z-score. So we're going to look up 0.975 on the chart, the z chart. So we're in the z chart here, 0.975. Oh, right here. 1.96, I do believe. Yep, 1.96 is the z-score corresponding to that alpha value. So what I do to get the x value, 5.4 times 1.96. It was a positive, so make sure you keep it positive. Go to mode 1, 5.4 times 1.96 plus 21 equals 31.58. Same thing we got on the calculator. So that rounds up to 32. TI users, same thing, inverse norm. Area is 0.975. Make sure you pay attention. The mean, oops, there we go. The mean is 21. And 5.4 for the standard deviation. And it gives us 31.58 also. So any way you do it, 32 is the answer. I'd highly suggest just typing in the normal CDF and be done with it. Sorry, the inverse norm, and be done with it. If you're looking for an area, use the normal CDF. If you're looking for a z-score, use the inverse norm. Questions on those? Okay. Another score type problem. We're trying to see who did better. So basically, we're going to convert both Billy Bob's and Cindy Lou's scores to standardized z-scores and see which one's better. So Billy Bob, he took the ACT. He made an 18. The mean for the ACT is 21. The standard deviation is 5.4. Cindy Lou Who over here, she took the SAT. She made a 955. The mean for that is 1059. And it has a standard deviation of 210. So I'm going to convert both of these, same formula as before. Just standard deviation times, oh, sorry, wrong formula. The other same formula as before, x minus mu over sigma. That's for both of these. 18 minus 21 over 5.4. See what that gives us. It gives us negative 5 repeating, negative 0.5 repeating, negative 0.5555. We're going to go 4 decimal places. Negative 0.5556. Let's see what Cindy Lou Who did over here. So 955 minus 1059 over 210. So on the quizzes, you just got it right or wrong because, well, I'm not going to go through and check partial credit on the quizzes, but on the tests, I will do partial credit. So if you kind of mess up and switch these around, I can still give you some partial credit on them. So make sure you show your work. And this one gives us negative 4.952. And surprisingly, something else that gave you guys a lot of trouble on this, you couldn't tell me which number was bigger. The bigger the z-score, the better. So which one of these is bigger? Cindy's bigger. Cindy performed, if you spelled that right, I don't know, better since her z-score was higher. Something simple like that'll work for me. And again, you can circle and point and all that good stuff because you're writing it on paper. Okay, I think we have about 4 problems left, maybe 3. Confidence intervals. So yeah, one of these was a undoable one on your quizzes, but again, that's not happening here. You're going to be able to do all these problems. You and your family are cuckoo for Cocoa Puffs, or you decided to buy some extra boxes to have on hand. Serving considered to be 1 cup. You decide to measure out exactly 1 cup and weigh your cereal before each meal. I guess you're OCD or something. The mean of 1 cup of Cocoa Puffs is 30 grams, with a standard deviation of 0.8 grams. Okay. That's my mean of the whole cereal chain Cocoa Puffs. On the 6th day, your family has eaten 72 servings of Cocoa Puffs. You really like your Cocoa Puffs. So N is 72. And you found that the mean weight was 29.8 grams. Think they're cheating you on your Cocoa Puffs? It might be. If possible, again, it is possible. Find the probability that the mean of 72 servings of Cocoa Puffs was less than 29.8 grams. Less than. Okay. No, not confidence interval rate. We're still in probability. Did I copy the confidence interval? I don't know. So look for the probability that's less than 29.8 grams. So that's my lower bound, 29.8. If you're using the calculator, you really don't have to worry about anything. Just type it in. Go to mode, distribution, normal CDF. Lower bound, well, it's less than that, so negative 1 times 10 to the 99. Upper bound, 29.8, 0.8, and 30. So P is 0.4013. And that's that. However, if you're doing it by hand, and I might add something to where I say show the standardized score first or something to make sure that you know your central limit theorem, we do need to find the z-score. X minus mu over sigma. However, central limit theorem tells us right here, if we got a sample size, divide by the square root of n. So that's what we do. Divide our sigma by square root of n. Anytime n is not 1, or even if n is 1, because it's not going to make a difference, that's what you use. Okay, so that's 29.8. So yeah, I think I will have you say, I'll say something like, give me the standardized z-score and find probability or something, because I want to make sure you can do this. And that z-score will be that, which is about negative 2.12. That's what we're going to look up on the chart. And it's z distribution. Negative 2.12. 2.12 should be this right here. Yep. 0.0170. So that's really, really, really different. Something went wrong on one of my calculations. Let me see what the TI gives me using the normal CDF. I might have typed something in wrong. Negative infinity. Yeah, we want the probability that it's less than, right? Less than, yeah. 29.8. I think I might have typed 28.9. No, that didn't make sense. The mean, 30. And standard deviation, 0.8. Oh, that's what happened. I didn't use the central limit theorem when I typed in the Casio, did I? So divided by square root of 72. Oops, whoa, no, that's not what I want. That should give me, yeah, okay. So let me go back into Casio. Sorry, guys. A little off today. The lower bound, upper bound, mean and standard deviation are the same, except the standard deviation has to be divided by square root of 72 for the central limit theorem. So negative infinity, 29.8. Standard deviation is going to be 0.8 divided by square root of 72. That's where I messed up. And the mean is 30. So that's what it gives me. So this, what I actually found was probably that one box of cereal was randomly selected and it had a weight less than 29.8 grams. That would be that probability. That's wrong. It would be this 0.0169 number right here. Don't forget central limit theorem. divide sigma by root n. Okay. So that's how you do it on the calculator. Same way, just don't forget to fix your sigma. Okay, now we have a confidence interval. So genetics and IVF Institute conducted blah, blah, blah. Okay, 92 babies. 73 of them were boys, so P hat is 73 out of 92. Conduct a 95% confidence interval. The confidence level 0.95. To estimate the yada, yada, yada. So here's where I like to draw my curves. Because it's 95% confidence level, that means I'm splitting this up into two pieces. I'm basically finding these z-scores here, where these are both 2.5%. So I need these z-scores here. If we look at our formula sheet, here's the formula. So we got to find the error first. So let's see. Error. And to do that, I need to look up z of alpha over 2. So alpha is going to be, well, alpha over 2, let's do that, is going to be 0.025. It's the complement of the confidence level, and we have to chop it in half. So on the Casio, we can easily just grab the inverse normal of that. 0.025. And I don't know why that's for that. Derivation of 1 and 0. That's standard. So 1.96. V alpha over 2 is 1.96. And we're actually going to use the positive and the negative, so we don't worry about the sign there. We just use the 1.96. The positive and negative would take care of themselves here. P hat, we got that. Q hat. It's the complement of P hat. So if I do 1 minus 73 over 92, that's going to give me Q hat. We just do 1 minus P hat. 19 over 92. Thought there were more intervals than that. Okay. That's P hat, Q hat, Z of alpha over 2. That's enough, and N. That's what we need to get error right here. So 1.96 times the square root of 73 over 92 times 19 over 92 over 92. Type that in the Casio. TI users, again, you got a little cheat for this. 1.96 times the square root, fraction side of fraction, And I believe that's right. 73 over 92, 19 over 92, 92, yeah. I'm gonna go ahead and store that value because I'm gonna use it a couple times. Store it to A. I get my error is 0.0827. But again, I'm not going to use the 0.0827. I'm going to use the whole decimal I can that I stored to the letter A. We don't round until the end. So now I do p hat minus E and p hat plus E. So I'm going to do 73 over 92 minus this number, and 73 over 92 plus this number. That's my answer. So plus, well, actually, sure, I can do the upper part first. Plus P so I get 0.876. And for these, we're going to go 3 sig figs, which pretty much just means go 3 decimal places. So 0.876 for the upper. Oops, I don't know why that happened. Okay, weird. And we also need to do the minus that E value, 0.711. So this interval here would be the answer. That's the confidence interval. That's the answer. So if you're doing it on the TI, you go to stat, test. We need to go down to the P interval. 1 prop Z int, that's A. X, that's the numerator here, 73. 92 for N, confidence level is 95%. Calculate, and we're done. 0.711, 0.876. Also gives you P hat, which you should already have anyway. Okay. So that's how you do a confidence interval. So let's look at this one. A random sample of 42 households was selected. So we'll go ahead and write down stuff. And the number of kilowatt hours was recorded. The average usage was found to be 327. In a very large study in the previous year, they found standard deviation to be 81. That's going to be our sigma. So they found sigma previously. This, if it was an S, if it was a sample standard deviation, it would be for this exact sample. It's for a very large study though. So we're going to use that as our sigma. Confidence level is 99%. So alpha over 2 is 0.005. 0.01 divided by 2 is 0.005. So now, look at your formula sheet. We got confidence interval for the mean. Do we know sigma or do we not know sigma? We know sigma. Okay, so this is the formula we need. Start with the error. So first thing I want to grab is z of alpha over 2. So let me get that z value. Put two tail, it's going to be corresponding to this 0.005. Go to my chart. 0.005 is 2.575. Using the Casio or the TI, you just do an inverse norm of the 0.005. Mode 3, number 3 again, 0.005, and leave those as standard. Negative 2.576 if you use technology. So it is slightly different already right there, but that's completely fine. Again, there's an interval of answers I accept, because you will get different answers if you use the chart or if you use the calculators. Let's see. So we got z of alpha over 2. We got sigma. We got n. Let's find out what E is. Oh, hey, somebody's joining now? Maybe. Oh, Jordan, you there? Oh, I got a bunch of messages now. Let me go through. Give me a minute. And let's see. Do you know what I'm busy, Lakin, sorry. Let me join back, Jared. Hello. Greetings. Let me try and invite Jared again, I guess. I think I have to stop the show for that. Yeah, here we are, right? Joe Bear, where are you at? There you are. Let's see, you might pop in. Okay, so let's go back to the confidence interval. We've discovered that it is a Z confidence interval because we know sigma. So we are about to calculate the error using our formula from the formula sheet. If you look on your formula sheet, confidence intervals are chapter 7. That tells you, we just did a P interval. Now we're doing a Z interval. Next, we're probably going to be doing a T interval. I think you'll have one of each on the test. This is what we're dealing with here, chapter 6 and 7. So error, 2.575 we got from the chart or using an inverse norm. Sigma, square root of 42. Calculate that, and that'll give me my error. Again, TI users, all I have to do is type in the information and you're pretty much done. So let's see. I can store that, but I'm not going to. 2.575. This is the answer you'd get if you were just using the charts and you didn't use an inverse norm. You will get slightly different values using the inverse norm. That's perfectly fine. So error is going to be 32.18. And I'm just going to write that down, but I'm actually going to store this entire value to A so I can do it without rounding. Instead of P hat, we're using X bar. So X bar plus and minus are error. So my answer is going to be 327 minus 32.18.